up our calendar and remind you that on Tuesday, next time I see you, we have a quiz. It'll be the group portion, individual portion like last time, and it's covering 1.5 to 1.9. So the demo and activities we're about to do right now will not be on the quiz, up through integrating factors. Is what? The next time I see you, yeah, the 28th. Yeah. Okay, let's jump to 2.1. This demo is really quick. So you should have time to go back and finish. If you did 1 and 2 in the activities from the last one, you're in good shape. And so once you get through 1 and 2, jump to the activities for this lesson. Okay, modeling via systems. So in many real-world situations, we have more than one dependent variable that interact with each other. And a classic example is the predator-prey model. We talked about this model in one of our earlier classes. We're going to do some more work with systems today. So remember, R of t denotes prey, like for rabbits, and F of t denotes predators for foxes. So we assume that R and F are both non-negative, because you can't have a negative number of rabbits or foxes. And then here's a system of equations that might govern the changes in the two populations. So if we look at the terms, there's 4 terms here. So if R prime just equaled 2R, right? Ignore the second term there. That says that the rate of change of the population is proportional to the size of the population. The constant of proportionality is 2. So this is the Malthusian model of population growth. And it solves, if you solved this using separation of variables, you would get R of t is c e to the 2t. It says that rabbits grow exponentially when there are no foxes, right? Right, because I'm ignoring the term that has the F in it. So when you ignore that term, rabbits would grow exponentially. And then for the F prime equation, if you ignore the RF term, so ignore the term that has an R in it, this would be F prime equals negative F. This is, again, just the Malthusian model. And except this time, our constant of proportionality is negative. This would lead to exponential decay. So this says if you were to solve that with separation of variables, you would get F of t equals, I'll say, k e to the negative t, different constant of proportionality. And so this says that foxes decline exponentially without rabbits. So far those two things make sense, right? The rabbits would grow exponentially without foxes because there are no foxes to eat them. The foxes will die out if there are no rabbits to eat. Yep.
That's not like actually solving.
Right, I haven't solved. Right. Yeah, I'm just looking at what each term says. So the 2R term, the 2R, that says that rabbits grow exponentially when there's no foxes. Right. Yeah, I'm not actually solving this. I'm just thinking about what each term is telling me. Yeah. And then RF is an interaction term, if you remember that. So it's just a way to measure how often they interact. If you multiply the number of rabbits times the number of foxes, as rabbits goes up or as foxes go up, they'll interact more, and the product of RF goes up. Okay. So RF is an interaction term, and it's negative for rabbits. It's not good for rabbits when rabbits and foxes interact, but it's good for foxes. So they have a positive interaction term, right? Positive for rabbits. Nope, sorry. Yeah. Positive for foxes, but negative for rabbits. So the coefficients are parameters that depend on the specific species involved, the environment they're living in, stuff like that. So I have just some random coefficients there. This system, like I solved when I took out the interaction terms you can solve, but it's actually impossible to solve analytically. You can't come up with a formula for R and for F, generally. But there are some solutions that are really simple. So for some initial conditions, like R of 0 is 0 and F of 0 is 0. So at time 0, there are no rabbits and there are no foxes. So what's going to happen? Nothing. There will always be no rabbits and foxes, right? So if you go up and look at the equations, if you plug in into the R prime and F prime equations, if you replace R and F with zeros, it says R prime is 0 and F prime is 0, which means neither population is changing, so they can't ever move away from 0. Right, right. So that's a simple solution, right? Are there any other initial conditions that lead to an equilibrium solution? Right, so the size of the rabbit population and the fox population never changes, constant. Right? If the size is constant, if R of t and F of t are constant, that means that the derivatives are 0. 0. So dr dt was 2r minus 1.2 rf, and df dt was negative f plus 0.9 rf, right? Double check it. Yeah. Okay, so I want to know when both of those are 0. When neither population is changing, their derivatives will be 0. So this is just two equations with two unknowns. I can solve for R and for F. So in this first equation, there's an R in both terms, so I'm going to factor it out. And I don't even need the other equation to solve this. This says R equals 0, or 2 minus 1.2 F equals 0, and then this is a simple linear equation. And you get F is 2 over 1.26. No, that's not right. I need a calculator. 1.6, yeah, 1.6, 1 2/3. Five. So, I mean, you can't have 1 2/3 of a rabbit, but maybe this is like, or of a fox, but this could be measured in like thousands or something. Negative, it's not negative. Move, yeah. Okay, so here I'm going to factor out an F, and I have negative 1 plus 0.9 R equals 0. And I get either F equals 0 or 0.9 R equals 1. So this is 1 1/9, which is 10/9. So I already knew the R of 0 and F, R equals 0 and F equals 0. That was one equilibrium solution, right? My other equilibrium solution happens when there are 5/3 foxes and 10/9 rabbits. Again, those numbers don't really make any sense in the real world. We're talking about thousands or something, right? 10/9 thousands of rabbits. So those are numbers where the rabbit and fox population live in a state of equilibrium. There are just enough rabbits to feed the foxes. There are just enough foxes to keep the rabbit population in check, and they just stay at those levels forever. So remember that the solution to a system is two functions, right? So f equals 5/3, that's not a number, that is a function, right? But it's the value 5/3 for all time. and R is the rabbits, and that stays at the value 10/9 for all time. All right, so that's it for the demo portion. Like I said, go back to the activities you were just working on